First thing I want to do is talk about the test. There's a test on Tuesday. So exam 1 is Tuesday. I think that's the 20th. Yeah. No, it's, closed notes, closed book, but I'll give you all the equations and all the conversions. And the topics will be first, units, and second, kinematics of particles along a line. And so the way to get ready for the test is to spend a lot of time working through those practice problems, these two sets of practice problems. I would say that you're ready for the test when you could explain how to do these problems to somebody else. So that means you're not memorizing the solutions, but you're able to think through, like, okay, here, now I list out these things. Now I know that this is moving in the negative direction, and so this is negative. And like, if you could explain at every step why you made the choice you made to get the solution for the practice problems, then you'll do great on the test. There won't be anything on the test that looks unfamiliar. Yep. No, that's only for the quizzes, those short answer questions. So, and there's a quiz today, so that'll be, but the quizzes are just based on the lectures, just reading through the lecture notes enough to remember that stuff. And then the exams are totally related to the practice problems, not the lecture. Yes?
Do your exam vocabulary go from beginning to where we are now, or is it from exam to exam?
Everything's cumulative, so everything goes from the start. So you got to keep refreshing the old stuff as we move through new stuff. Yes?
So the stuff that we started learning last time, the two-dimensional stuff, isn't going to be on the test?
That's right.
Okay. Thank you.
And yep, sure. And so today I'll take questions if anyone has questions, and then we're ahead of the night class. So I just want to spend today working through example problems, or I'll put up example problems, give you time to work on them, and then I'll go through them. That's all I'm going to do today, stuff to help get ready for the test. Any other general questions or questions about the test?
Yeah. Are the solutions to the work problems on the
Yes, they are, except now that you mentioned that, I think there are 3 questions on kinematics along a line that aren't posted. But I have them, so I'll get those up. But so everything will be up, yeah. Any other questions? Okay, how about any specific homework questions that you'd like me to explain? Anything? No. Okay, well, I'll start with the first example problem. I'll write it up, give you time to work on it, and you can work through it together. If you get stuck, maybe the person next to you can help you go through it. And this is the kind of stuff that's going to be on the test. Okay, so for the first one, there are these, yes? Yes, they are too. Everything in this class is cumulative. The lab exams too. So let's say there's these 3 locations, A, B, and C. and they're each half a meter apart. And an object starts at C, it reaches B in 1 second, then it reaches A in another second, then it reaches B in another half second. So the first thing I want you to do is draw a position versus time graph where time equals 0 is when the object starts to move. Position equals 0 is at A, and the positive direction is to the right. All right, so this kind of question is very, very, very likely to be on the test. So just that might be underselling how likely it is for a problem like this to be on the test. Okay, so the motion goes like this. It starts out here, it goes this way, turns around at A, and then back to B. This is at 0 seconds because we said 0 seconds was when the motion starts. This is at 1 second. This is at another 1 second. And then this is at another half second, so this is at 2.5 seconds. And now the positions, our position equals 0 is A, so A has a value of 0. The positive direction is to the right. And so if B is 0.5 meters in the positive direction from 0, what's the value at B? Yeah, 0.5, positive 0.5. And if C is another 0.5 meters in the positive direction, what's the value there? 1, yeah. So now I'm just going to plot these points. That's position. That's time. The times that we have are 1, I'll spread it out a little. 1, 2, 2.5. And the positions that are going to come up are 0, 0.5, and 1. And now I'll just plot these points. At 0 seconds, the location of the particle is at C, which is at 1 meter. At 1 second, the location is at B, which is well, I shouldn't have I just labeled that wrong. This is meters. So at 1 second, it's at 0.5 meters. At 2 seconds, it's at 0. And then at 2.5 seconds, it's back at 1. And then just draw a line through that. It doesn't matter what kind of line you draw through it. Anybody have any questions about how I did that? Yeah?
You said at 2.5 seconds.
0.5. I'm sorry. I know that makes it more confusing when I mix my words up like that. At 2.5 seconds, it was back at the point B, and B is at the location 0.5 meters. Yes?
So on the position side, you don't want like A, B, C label or anything like that?
Nope, just the numeric labels.
And do you want the top graph also drawn besides position versus time?
No, I don't care about that, but I think that's a helpful way to do it if you're looking for a way to think through it. Yep. Any other questions? Okay. So now, part B, draw position versus time graph. But this time, the object starts moving 5 seconds after our chosen time equals 0. The position equals 0 is at B, and the positive direction is the opposite way, to the left. Okay? So you can really think through it the same way, but draw another position versus time graph. So I'm going to go through this the same way. I think if these totally make sense to you, then keep doing it the way you're doing it. But if you're having trouble figuring out how to go with these, I think this approach is always a good way to do it. So I'm going to just take this number line. And I'm going to draw the motion again. The motion starts at C, passes B to A, and then back to B. And now we can think about when these things happen. When does it start at C? When does it get to B? When does it get to A? When does it get back to B? It starts moving 5 seconds after time equals 0. So this instant at the start of the motion, what's the time? Yeah, 5 seconds. And now it takes 1 second again to get from C to B. So this happens at 6 seconds. 1 more second to get to A, so that's 7 seconds. And half a second to get here, so this is 7.5 seconds. Any questions about that? And now we have to think about the positions. So that's based on the position equals 0 and the positive direction. The position we're choosing to be called 0 is at B. So B is there. The positive direction is this way. Well, we know that the point A is half a meter in the positive direction from 0. So what's the numeric label for A? Yeah, positive 0.5 meters. And point C is half a meter in the negative direction from 0. So what's the label for that one? Yeah, that's negative 0.5. And now we can just read these values off of the number line and put them onto the position versus time graph. So there's position, there's time. The times that we're going to deal with are 1, 2, 3, 4, 5, 6, 7, and 7.5. And the locations we're going to deal with are 0, positive 0.5 meters, and negative 0.5 meters. When time is 5 seconds, what's the position of the object? Negative 0.5, yep. So that's the first point. Then when time is 6 seconds, what's the position of the object? 0. When time is 7 seconds, what's the position? And when time is 7.5 seconds, what's the position? 0. And so the graph looks like that. Just as far as sort of an overall qualitative understanding of what's going on, well, they look a little different because I made the numbers bigger on this one than I did on the other one. But basically, all these things is they're shifted horizontally, they're shifted vertically, and they're flipped. Okay, so what was it that shifted this graph horizontally compared to the other one? It's the horizontal one, the shift along the time axis comes from putting in that extra 5 seconds. So changing what we called our time equals 0 instant. And then the vertical shift, comes from giving a new position equals 0 location. And then what causes the flip? The positive direction, yep. Any questions about that?
Could you repeat that, please? Like
Those three things, yeah. The horizontal, and this isn't something that should really influence how you solve these problems. It's more just like an overall understanding, I think. Maybe you could use it as sort of a check when you get done to see whether your answer makes sense. But it's going to be shifted horizontally if you choose a new time equals 0 instant. It's going to be shifted vertically if you choose a new position equals 0 location. And it's going to be flipped if you choose the other direction to be positive.
Okay, thank you.
Sure. Anybody want to do one more like this, or? Yeah, one more. Overruled. So it does appear to me, from my observations of human faces, that a few people in this class have found something that they need to study a good bit before Tuesday. But that's good. Like, what you want is you want to know what stuff you have to study to make a difference. You know, the thing you hate is like when you put all this time studying and none of that stuff was on the test. This is stuff that is very likely going to be on the test. Okay, so part C. So do a position versus time graph again. Let's say this time it starts moving one second after the time equals 0 instant. And the position equals 0 location is going to be at C. And the positive direction is going to be the original one, going to the right. Work together on this and like trash talk each other. Like if the person next to you can't do it, be like, it's your problem. Let me go through this one. So the motion is still the same. None of this stuff changes the motion. It just changes how we observe it. So it's still going C to B to A, back to B. Now for the times, what's the time when it starts the motion? Yep. When it gets to B, that's 2 seconds. When it gets to A, that's 3 seconds. And then another half second, so 3.5 seconds. And for the labels, our position equals 0 is C. The positive direction is this way. So B then is half a meter in the negative direction from 0. So what's the label for B? Yeah, negative 0.5. And another half meter in the negative direction, what's the label for A? Yeah, negative 1 meter. So the times that we're going to deal with are 1, make it a little bigger, 1, 2, 3, 3.5. And the locations we're going to deal with are 0, negative 0.5, and negative 1. When time is equal to 1, the location is 0. The position is 0. When time is equal to 2, the position is negative 0.5. When time is equal to 3, the position is negative 1. And when time is 3.5, the position is negative 0.5. Any questions about that one? Okay. Well, let's do a constant acceleration problem. Let's say that a ball bounces off the floor to a maximum height of 2 meters. So the first question is, how fast is the ball moving when it leaves the floor? Okay, work together on that one. So the first thing we have to do is specify those 4 things. Time equals 0, time final, position equals 0, and positive direction. What do we want to choose as the instant for time equals 0? Yeah, right when it leaves the ground. Yep. And then what about time final?
At the 2 meter height.
That's right. For position equals 0, I'm going to choose the floor. Like I've said before, that's arbitrary, but you could screw it up if you really tried to. So floor. Positive direction, this is free fall, so I'm going to make that up. And now let's think about what we know and want. Do we know time final? No. Do we want it? Nope. Do we know acceleration? Yeah, it's free fall. So acceleration is negative 9.81 meters per second squared. Do we know initial position? Yeah, it starts at the floor. That's our 0 position, so this is 0. Do we know P final? Yep, it's 2 meters in the positive direction from our 0, so that's positive 2 meters. Do we know the initial velocity? No. Do we want it? Yeah, that's what we're trying to find. And do we know the final velocity? Yeah, the final time is when it reaches the highest point, so we know at that instant the velocity has to be 0. Is there an equation that'll work with these? Yeah, there's no time final anywhere, so we know if anything works, it has to be this one. So we have 2 times negative 9.81 meters per second squared times the quantity 2 meters minus 0 is equal to 0 squared minus v initial squared. If we multiply all this first on the left side stuff together, that is negative 39.24 meters squared per second squared. And that's equal to negative v initial squared. What? The negatives cancel. And so take the square root of both sides. What do you get if you take the square root of 39.24? Okay, so 6.26. You also take the square root of the meters squared per second squared, which gives you meters per second. This is equal to VI. And remember, when you take that square root, that's plus or minus, so we have to think about that. Do we want the positive or the negative? Positive, because when it leaves the floor, it's moving in the positive direction. So that's the answer. Yes? Yes, I want you to go all the way through the units calculation on the test. After we're done with this test, when we go to 2 dimensions and stuff, you can be more relaxed about that. But for the motion along a line, I want you to carry the units all the way through. Yes?
I'm sorry, can you explain one more time why the acceleration is always negative?
Yeah. So when something's in free fall, the acceleration is always downward because that's the direction that gravity pulls on it. But to make sense out of it, think about the fact that when an object is on the way up, it's slowing down. So its velocity is that way.
Yeah.
If it's slowing down, that means its acceleration has to be the other way.
Okay.
So on the way up, we know the acceleration has to be down. And then on the way down, it's speeding up.
Yeah.
Its velocity is down. And if it's speeding up, that means the acceleration also has to be down.
Okay.
So
Always negative.
So it's always negative. Yep. And it's always 9.81 negative. Mm-hmm. All right. Any other questions about that one? So now, how long is the ball in the air before it hits the ground again. So from the instant that it leaves the ground until it hits it again, how much time is that? Okay, what do you think about changing the time equals 0? Is there any reason to change that? You could do this problem by doing it from the highest point, but it ends up just taking a lot of time, and it's a harder way to do it. You can do it that way, but don't do it that way. So time equals 0, that's still going to be when it leaves the ground. Time final is going to be when it hits the ground on the return. Position equals 0, I'll still make that the ground. And the positive direction I'll still make up. We're trying to find the time final. The acceleration is negative 9.81. The initial position, that's when it leaves the ground, so that's 0. The final position is also 0 because it's landing back on the ground. The initial velocity, now we know that that's positive 6.26 meters per second. Do we know the final velocity? No. We don't care. So the equation that works, I think, is P final is equal to P initial plus V initial time final plus 1/2 A T final squared. So that says 0 is equal to 0 plus 6.26 meters per second times time final minus 4.905 meters per second squared times time final squared. And we can add this negative 4.905 TF squared to both sides. And that gives us that 4.905 meters per second squared time final squared is equal to, how do I want to do this? Maybe that's not the way I want to do it. Let's think about it this way. Sorry about that. So this is a quadratic equation, right? 0 is equal to 6.26 meters per second TF minus 4.905 meters per second squared times TF squared. You could use the quadratic formula for this. Or if you remember this stuff and notice that both of these have a TF, you could factor out a TF and write this as TF times 6.26 meters per second minus, let me make this a square bracket, 4.905 meters per second squared, TF. And now there's two roots to this. TF can be 0, or it can be 6.26 divided by 4.905. Can someone tell me what that is? 1 point something. 276. What? No? Okay, so there's two possibilities. If you don't like that way of doing it, just plug it into the quadratic formula. Which one of these do we want? Yeah, we want this one. What's this one telling us? Yeah. Well, yeah, this is the one that says, oh yeah, I know when it hits the ground, right at the start when it leaves the ground. So that's referring to as it leaves the ground. That's not the one we're looking for. We're looking for the one when it comes all the way back. Okay, now I'm not going to do this calculation, but does anyone have, we figured out how fast it's going when it leaves the ground. We figured out its velocity. Anyone have a feel for how fast it's going when it hits the ground again? Well, we could do it. Yes, that's exactly right. So we could use this expression. So V final is equal to 6.26 minus 9.81 meters per second squared times 1.276 seconds. And we get that the final velocity is negative 6.26 meters per second. And with constant acceleration, that's just a fact of how it always happens. If you shoot something up into the air, at every height along the way, the speed going up is the same as the speed going down when it returns to that height. Yes?
So, I use that, or knowing that I use the first equation, the final equals the initial acceleration times time final.
Yep.
I use that to find how many seconds it would take if you get at the halfway point.
Yeah, that works great.
If I did that on
Yep, that's fine. You just have to be sure that you're talking about those two instants being the same height. Like if that ball had been launched from a different height, you couldn't do it that way. Okay, so this is like a public service announcement. Like this is why, like, you know how on Easter, at noon on Easter, you go out and shoot guns into the air to celebrate? Like this is why that's a bad idea. Because, I mean, that's neglecting air resistance, but if you shoot a bullet up into the air, if you ignore the effects of air resistance, which are significant, but when the bullet gets back to the height that you shot it, it's going exactly as fast as it came out of the muzzle, which is a dangerous speed.